We continue our discussion on widebanding by using an inductance. The circuit that we were considering is that of a shunt peaking. We have a current source I sub S, L and R. This goes to the base of a transistor Q, R sub L, and this is I0. The current is I0. And by drawing the equivalent circuit, we had shown that the current transfer function AIS, which is equal to I0 by IS, is of the form K S plus Z divided by S squared plus AS plus B, where K is equal to minus GM by CT, minus GM by CT, Z equal to R by L, A is equal to, I don't remember, R plus Rx divided by L plus 1 over R pi CT, and B is equal to R plus Rx plus R pi divided by L R pi CT. Okay. This is the transfer function, and by taking the magnitude squared, we had reduced it to the following form: AI j omega magnitude squared. We had reduced it to the form k squared z squared divided by b squared 1 plus, did you do this? Omega square by z square, and then 1 plus omega squared s squared minus 2b divided by b squared plus omega 4 divided by b to the b squared again. Okay. And you notice that this quantity obviously represents the gain magnitude squared at omega equal to 0. Isn't that right? Omega equal to 0, this quantity becomes 1. So I can write this as AI j0 squared multiplied by the same quantity. And if I take the normalized value AI j omega divided by AI j0 whole squared, then this becomes 1 plus omega squared by z squared 1 plus omega squared s squared minus 2b divided by b squared plus omega 4 divided by b squared, where AI j0, the value, if you substitute the values, it becomes minus beta 0 r divided by r plus rx plus r pi. You have to substitute for k, z and b, and this is the value. We shall require this later, AI j0. This is the gain, mid-band gain, or it starts from low frequencies because there is no coupling capacitor in this circuit. Yes. Oh, beta 0. Beta is the same as beta, GM R pi. I should not use beta 0. Beta is GM R pi. Okay. Now, the question that we had left unanswered is, what should be the relative values of A and B? What should be this coefficient in order that this magnitude squared function is maximally flat at omega equal to 0. So what we want to do is, let's call this as m squared, m omega squared, magnitude, normalized magnitude squared. What we want to do is, if I want maximally flat, I want dm d omega equal to 0. We wish to have, and we wish the next differential coefficient also equal to 0. If possible the third, fourth and so on. Okay, as many as possible. Now how many should be possible? You see, 2 or 3? only two are possible. The third automatically comes, as you will see. The third automatically comes. All right, let us see. I can write, the way to visualize this is, it's a rational function. M squared omega is a rational function. You convert this into an infinite series. That means what you do is you divide 1 plus omega squared by z squared by 1 plus omega squared s squared minus 2b divided by b squared plus omega 4 by b squared. Divide the numerator by the denominator. Make a long division. And naturally the quotient would be an infinite series. Isn't that right? Quotient would be an infinite series. Well, another way of looking at this is, write this as omega squared by z squared multiplied by 1 plus omega squared s squared minus 2b by b squared plus omega 4 by b squared to the power minus 1. And this is an infinite series. Multiplying by this obviously shall be an infinite series. What would be the constant term in the infinite series? 1. And the coefficient of omega squared would be 1 by z squared minus this, right? Then there would be a coefficient of omega to the 4th and so on and so forth. Now let us look at this. M squared omega, if I write as an infinite series, my expression becomes 1 plus omega squared 1 by z squared minus s squared minus 2b divided by b squared plus etc. Obviously there would be an omega 4th term, and you can find out the coefficient and so on. Okay. Obviously dm d omega is 0 at omega equal to 0, because this becomes 2 omega 4 omega cubed, and put omega equal to 0, it becomes 0. Obviously no effort is needed. But suppose you want to make d2m d omega 2 also equal to 0 at omega equal to 0, then it requires, after second differentiation, this will be left with 2 multiplied by this constant. So this constant has to be equal to 0. So this is the condition, 1 by z squared equal to s squared minus 2b by b squared. This is the condition that is needed for the second order flatness. As far as the next differentiation is concerned, you see 4 omega cubed, 12 omega squared, then 24 omega, obviously that is automatically 0 at omega equal to 0. The degree of the rational function is 4, isn't that right? The rational function that we started from, the highest power is 4, and in general this is true, that if the degree of the rational function is 4, then the maximum possible number of flatnesses is the degree minus 1, third order of flatness. Okay. And it is also true, now note this very carefully, it is also true that if I can write a normalized function like this with a constant equal to 1, okay, then the condition for maximal flatness is that the corresponding coefficients in the numerator and denominator should be equal as far as possible. Okay. For example, here we have found out that the condition for maximal flatness is 1 by z squared equal to s squared minus 2b by b squared. The next coefficient is 0. Obviously 0 cannot be equal to 1 by b squared, because then b requires to be infinity. So the maximal flatness condition is that the corresponding coefficients, you see 1 and 1, as much as possible, the next one is omega squared, I can make them equal, but I cannot go further. So this is the condition for maximal flatness. If this was an 8th order function, then maximal flatness would have demanded that up to omega to the 6th the coefficients are equal. Okay. We will see, we will come to this another example of condition for maximal flatness a little later. But this condition s squared 1 by z squared equal to s squared minus 2b by b squared is the condition for maximal flatness in the magnitude. So it is called MFM condition, MFM condition. And under this condition, the omega h, now what does this mean? It means that if you permit no peak in the frequency response, no peaking in the frequency response, then this gives the maximum possible value of f sub h. Agree? It gives the maximum possible value of f sub h. If this condition is not obeyed, then it will go either peaking or it will come down in a less flat fashion. It will come down more rapidly. So the maximum possible omega h is obtained under this condition, and this can be obtained by putting m squared omega h equal to, the value of omega h can be obtained, not root 2, there is a square here, so it should be equal to half. But you see, which means that omega h squared by z squared divided by 1 plus, should I write a square minus 2b by b squared? No, that is not needed. I can write omega h squared by z squared, that simplifies calculations, plus omega h to the power 4th divided by b squared. This should be equal to half, and obviously this will give you a 4th order equation to be solved, but fortunately this is a quadratic in omega h squared, and therefore you can solve for omega h, and the final result is the following. Simplified result is omega h equals to half b by z whole squared plus, actually you will have two, quadratic equation has two solutions. One of them will come out negative, the other will positive. Omega h squared cannot be negative, so the choice is unique. This is the plus sign we have to use, and then we have 1/4 b by z whole to the 4th plus b squared, this total quantity to the power half. Half is, the reason for half is obvious because we solved for omega h squared, okay. And one should remember that b by z is equal to rx plus r pi plus r divided by r pi ct, and one should also remember the value of b, which is r pi plus rx plus r divided by l r pi ct, okay. So you can find out omega, and the other equation that is required for design is ai0, which is equal to, as I already mentioned, beta 0 r, I'm sorry, I keep on writing beta 0, beta r divided by r plus rx plus r pi. These are the two equations that are needed for design of this amplifier for a given omega h and for a given mid-band gain. For a given mid-band gain. We will work out an example to illustrate this. Any question on this? These are our design equations, and now we can proceed. Suppose it is given that C mu equal to 5 puff, beta equals to 50, a rather low beta, GM is equal to 0.2 mho, which means that R pi is equal to 250 ohm, isn't that right? Beta and GM are given. Sometimes the quiescent collector current will be given. If that is given, then you find out GM as IC by 25, IC milliamperes divided by 25 millivolts, okay. Then Rx is given, Rx there is no way to derive it, it has to be given, measured. C pi, many a times C pi will not be given, but Ft will be given, and if that is the case, then you know omega t is equal to 1 over R pi C pi plus C mu. This is the transition frequency or unity gain frequency. C mu is given, omega t is given, R pi is derived from the value of GM in beta, and therefore C pi can be found out. Alright, C pi is given here, and RL is 500 ohms. This is given. The mid-band gain needed AI0 is required to be 25. Design this circuit. Design this circuit and find what FH does it obtain. What is the high frequency cutoff?
So isn't FH one of the design considerations?
It may be, it may not be also. We will work out another problem in which FH and midband gain are given, or FH is given, you are required to find out the midband gain. You see, as far as the gain is concerned, the absolute value of gain is not very critical, it's not very important. Okay? What is important is up to what frequency can you go. Now, this constraint that 25 should be the midband gain, this makes it 25 equal to beta r divided by r plus rx plus r pi. Rx is 100 ohm, r pi is 250, beta is 50, and therefore you can find out r. Capital R is the series resistance of the inductance, capital R, and capital R comes out as 350 ohms. To find the inductance L, yes.
So this capital R is not a discrete element, it's a part of the inductor.
It's a part of the inductor, that is correct.
So while designing the inductor, we are assuming that this is the maximum resistance it can offer.
It cannot, it should not get more than this. Now, in practice, suppose your capital R, suppose the coil can be made with less value of inductance, all right, then you can either redesign the circuit. That means you say you are asking for a gain of 25, I will give you more. You are asking for an FH of so many mega radians per second, I will give you more. The people would be happy, provided that is not in the frequency range which you don't want. Okay. Now, if it is a strict specification, that is you have to use R equal to 350 and the actual R that you get in series with the inductance is less, then you add a small resistance there. Okay. So, capital R is 350. Now, the next question is to find L. L will be given by the maximal flatness condition, that is S squared minus 2B should be equal to B by Z whole squared. L would be obtained from this relationship. And if I write down the expression for A and B and Z in this, I get an equation like this. R plus Rx divided by L, this is A, 1 over R pi Ct, S squared, minus 2B, B is R plus Rx plus R pi divided by L R pi Ct. This should be equal to B by Z whole squared, which is R pi plus R plus Rx divided by R pi Ct whole square. This is the equation. And if you look at the equation, obviously, yes.
Should be capital R.
Where did I write smaller? Oh, I am sorry. This should be capital. Thank you for pointing this out. I know capital R. I know it's 350. I know capital R. I know Rx. I know Ct. Ct is C pi plus C mu 1 plus GMRL. Okay. I know everything here except L. And that L occurs in a quadratic equation. Isn't that right? There is a squared here, so it becomes 1 by L squared, and this is 1 by L. So you can solve for 1 by L from this as a quadratic equation. There will be two solutions. Most probably one of them will not be acceptable and the other will be acceptable. If both are acceptable, there are situations when both are acceptable, then you can use either of them, but when you put in the circuit, one of them will satisfy, the other will not. Then it becomes slightly difficult. But in most of the situations it will be obvious which value is acceptable. Now, if you substitute all the values and solve for this, this requires crunching out numbers, and all practical problems you have to crunch out numbers. Okay? There will not be an SCDR to round off the values such that the gain becomes 40 or 23 or something. So, you will have to do this, and I can tell you it took me quite some time to calculate it out. 27.23 microhenry. This is the order of inductance that is needed, and 27.23 microhenry is not very difficult to make. Also, from the equation, now our design is complete. Okay, our omega h was not specified; it was required to be found out. So you substitute the values of the quantities b by z, which we have already found out, plus square root of 1/4 b by z whole squared plus, not whole squared, whole to the 4th, plus b squared whole to the power half, and this comes out as fh comes out as 2.76 megahertz. Our gain was 25. Our gain was 25, mid-band gain. So the GBW, gain bandwidth product, that we have achieved is 25 multiplied by this, which comes as 69. What would be the unit? Megahertz. 69 megahertz. Compare this with FT. FT is GM divided by 2 pi, don't forget the factor 2 pi, C pi plus C mu, alright. This calculates out to 398 megahertz. Okay, so approximately we have gone up to 20% of FT. Our GBW has gone up to 20% of FT. Is that clear?
How did you get GBW?
How did I get GBW? I multiplied this by 25. The mid-band gain multiplied by the bandwidth. That is the gain bandwidth product. It's 69, and it is still within very safe limits. In theory, one should be able to go right up to 400 megahertz. If your gain is 1, we should be, in theory, you should be able to go up to 398 megahertz. But things conspire to bring it down. Even with the use of an inductance, we can go only up to 69 megahertz. If we did not have an inductance, then it would have come drastically down. Okay, it is the inductance which has extended the bandwidth to 69 megahertz. Now, we consider a problem. The problem concerns a series peaked circuit. I shall indicate the basic steps and you work out the rest. In a series peaked circuit, the inductance and its losses, the coil, is connected in series with the base rather than in shunt. So we have a current source RS. It can be a current source or a voltage source. Okay, I have included a source resistance. So, and then you have the inductance L and its resistance R. This is the coil. This is the coil, and this goes to the base, and then you have an RL. The current is I0. The problem is GM is given as 0.2 mho as in the previous circuit. C mu is 5 puff. It's the same transistor which is being used for series peaking. 5 puff. C pi is 75 puff. Rx is 100 ohms. Beta is 50 and RL is 100 ohm. Now in the previous case it was 500, isn't it? What was RL in the previous case? Was RL effective? No, it doesn't depend on what RL is, because our transfer function is current transfer function. Current is GMV. Okay. Now what you are required to find out is design this circuit for maximally flat magnitude response. Here we don't care about the mid-band gain, but we care about omega h. Omega h is required to be 2 times 10 to the power 7 radians per second. These are the specifications, and then it says find out the mid-band gain. Mid-band gain is not a requirement, but in general the design problem, in practical design problem, both mid-band gain and omega h are specified, and then you will have to work under those constraints. Okay. Now if you draw the equivalent circuit in a routine manner, what you get is Is Rs plus minus and then a series Rs, then you get L, R and Rx. We take account of this because it is possible to take account, alright. Then we have R pi, and let us say we take Miller effect into account, and this is Ct. Ct is equal to C pi plus C mu 1 plus GMRL. Someone said it does not come into effect, the load resistance, it does in Ct, right, in the total capacitance it does. Then you have, this is V pi, then you have GM V pi and RL, and this is the current I0. We have ignored here the loading effect of C mu, we have ignored here, but in a strict sense, if RL is, for example, very large, if RL is very large, if the impedance of RL is comparable to that of C mu, then you cannot ignore C mu. In fact, we will see occasions where this time constant will also have to be taken into account. But continue with this analysis. If you analyze this, it is very simple. I0 is minus GM V pi, find out V pi from here and then put it in the appropriate form. The form that comes is the following: I0 by Is which is A sub Is, the current gain, that can be put in this form: K divided by S squared plus As plus B. Note the difference where, let me put down the constants first. K is equal to minus beta Rs divided by L Ct R pi. A is equal to small r divided by L. What is small r? Small r is the series combination of all the three. Big Rs, big R plus small Rx. Small r is the combination of these three resistances. They all come in series, so you can combine them. Plus 1 over Ct R pi, and B is equal to R plus R pi divided by L Ct R pi. Okay. The current gain is an expression K by S squared plus As plus B. The next thing we do is we want maximally flat magnitude response, and therefore we take the magnitude and put it in the form in which the numerator as well as denominator starts with 1. Okay. So I get Ai j omega divided by Ai j0 magnitude squared as 1 over, well, let me put down what is Ai j0. That is equal to minus beta Rs divided by R plus R pi. I am omitting these algebraic steps. I can write this as 1 plus omega squared S squared minus 2b divided by b squared plus omega fourth divided by b squared. Now tell me what is the difference between this transfer function and the previous one? There was in the numerator, there was a 0 in the previous case. Okay, there was a 0 at S equal to minus Z minus R by L. How did this 0 come? Because the inductor was shunting, and at S equal to minus R by L, the inductor and series combination was behaving as a short. That is how the 0 came. Here there is no 0 because there is no shunting effect. Okay. that obviously changes the maximal flatness condition. What will be the MFN condition now? Pardon me? S squared equal to 2b, as simple as that, because the numerator coefficient is 0. I can't make 1 by b squared equal to 0. So this is the maximal flatness condition. And if I put this in terms of the elements, then my condition becomes L plus Ct r pi whole squared equal to twice r plus r pi L Ct r pi. This is one. And under this condition, what would be omega h? What would be omega h? Look at this expression. This becomes 0. So the magnitude squared becomes 1 by 1 plus omega 4 by b squared. So this should be equal to 1. So omega h should be equal to square root of b. That's it. As simple as that. Which is equal to square root of r plus r pi divided by L Ct r pi. These are your design equations. And of course the other is Aij0 is equal to minus beta Rs divided by r plus r pi. Suppose these are your design equations 1, 2 and 3. Suppose omega h and Aij0 mid-band gain are specified, then you can find out a relationship between r and L. Isn't that right? If omega h is specified and Aij0 is specified, this contains small r, this also contains small r, and therefore you will get a relationship between small r and L. Okay? You have to substitute that here to obtain the value of required value of L. Here omega h has been specified. What else? Pardon me? Oh, the other things are specified. So only specification here is omega h, and therefore from here you get a relation between L and R, which you substitute here to get the value of L, the numerical values. I shall only give you the final results. The final results are, I have gone through this quadratic equation and all that. Final results are that R plus Rs is 26.92 ohms. Capital R represents the loss in the inductor, and Rs is the internal impedance of the source. Okay, R plus Rs. So obviously Rs would be a low value, and you are right, the current source actually is a voltage source. Okay, low valued resistance shunting a current source means a voltage source, and the inductance required is 20.94 microhenry, and Ai0, the mid-band gain under this condition, is approximately 3.57 only, which means a gain bandwidth product GBW is 7.14 mega radians per second, the gain bandwidth product, whereas omega t is calculated at 2500 mega radian per second. Series peaking therefore is not as efficient as shunt peaking. This simple example demonstrates. We will continue this discussion next time.